Hello, welcome to this 8th class in this physics of materials lecture series. So, we have now through our earlier classes built a framework for this course and also started building models for the material for various properties of the materials. More specifically, we have focused on the metallic systems, and so our focus will continue to be metallic systems, and where possible we will generalize to other materials. In the last class we started developing, in the last couple of classes in fact, we have started putting together the framework for what is considered as the Drude model for the materials and specifically for the conductivity, and it is a model that is attributed to Drude and Lawrence, and the basic idea is simply that we take the ideal gas kinetic theory of gases rules and apply it to electrons in the solid. We treat them as free electrons which run through the extent of the solid and see what is the behavior of these electrons that we can predict. Specifically in the last class we looked at the electronic conductivity process and we tried to see what would happen to the electrons in a solid if you apply a potential gradient across it and how they would respond to it. What are the processes that would then slow the movement of those electrons, in other words the collisions that they would have with other electrons present within that system, and what is then the equilibrium that the kind of static dynamic equilibrium that exists within that system, and then how the electrons are moving as a result of this potential gradient that exists. So they continue to move, they reach some kind of a velocity that which is the average velocity with which those electrons move. So this is the kind of system or the model that we are building, and as I mentioned, this is the Drude model. Today we will take this model forward. We will try and explain one more of the material properties, which is the thermal behavior of a material, using the same framework which is what is being employed for the Drude model. So that is the basic idea that we will explore through this class today. So if you look at thermal properties, essentially conductivity or heat conduction, if you want to transport heat, then this is actually a phenomenon that is very important from an engineering perspective. There are a lot of places in engineering and in technology where heat transfer is a very critical aspect of the functioning of that technology. Okay, so it is a very important aspect of the functioning of the technology, heat transfer, and so a lot of it has been studied quite extensively. If you look at literature, it has been studied very extensively. If you look at heat transfer in general, then there are three modes by which heat can be transferred from one location to another, and they are conduction, convection, and radiation. So we have three principal modes by which heat can be transferred from one point to another, and they are simply conduction, convection, and radiation. So in all engineering, in an engineering sense, anywhere you run into the heat transfer processes, you will see one or more of these in effect playing a role. So when we talk of conduction, it is a process where heat is getting transferred due to direct contact of the material, okay, with something else. So atom to atom contact is there. We are not really looking at atomic movement in the sense of a movement of atom from over any large distance, so to speak. They are all atoms which are sort of frozen within their, not frozen, but they are in fixed positions relatively speaking in a lattice, and then heat is being transferred across through those atoms, or also through the electrons which present within the system. So in fact in highly conducting materials, high thermal conductivity materials, often the heat is being transferred through the electrons that are moving through the system. In less conducting materials, the transfer of heat is occurring through atomic vibrations, where each atom's vibration is then being partially being transferred to its neighbors and so on. So in that process the heat gets the energy gets transferred from the hot end to the cold end. So, but the basic idea being largely the atoms are in fixed positions. So, there is no, so this is typically a process that we associate with a solid. So, conduction is a process that we would normally associate as the primary manner in which heat is being transferred from one end of a solid to another end of a solid. So, it is within that solid whatever is happening, that is the kind of heat transfer that we would refer to as conduction. Okay, so this is within a solid. In general, this is what we are looking at. So, within a solid is a good example of where you are looking at for conduction. Okay, so conduction is in that it is in that context that we most often talk of conduction. Okay, then we have convection, which is something that we associate normally with liquids and gases. Okay, and here the transfer of heat is occurring due to a fairly large scale atomic movement. So, it is in that sense that it is distinctly different from the conduction process. So, if you take for example a beaker containing some liquid and then you slowly heat it up. So, you have a beaker here and some liquid and you very slowly heat it up. Very slowly heat it up, what will happen is the temperature of the liquid very close to the bottom of this container will go up. In general, this also means that the density of this liquid very close to the bottom of this jar of this beaker, the density will go down because the liquid will expand. Okay, so density will go down, there will be colder liquid on top which is now of higher density, and so the colder liquid will try to move down and the hotter liquid will try to move up. Okay, so in this process you will have the liquid getting mixed up, and this is going to occur in a very slow and gradual manner as you depending on how slowly you introduce this heat into the system. Okay, so gradually this is what is going to occur within the system, and so slowly this liquid gets mixed up simply because you are providing heat at one location. Okay, so therefore it gets mixed up. So, such a mixing up of a liquid or a gas as a result of this thermal differences that exist between one region of this liquid and another region of this liquid, such a process of mixing up we refer to as convection. Okay, so this is the, so as I mentioned, largely this is something that we associate with liquids and gases, and to the extent that it occurs in the manner I have described, it is something that we would refer to as natural convection. Okay, so if you did nothing else and you just provided heat from one end of a container containing a liquid or gas, simply because of density differences that will arise within the system, the liquid or gas will now start getting mixed up, specifically due to these density differences. Such a process is then as I mentioned referred to as natural convection. In an engineering sense, often if you want convection in any as a significant form of heat transfer, if you want to ensure that some heat transfer is occurring and you want it to occur as quickly as possible, as well as possible, and so on, or you want to speed up the process, then normally in an engineering sense or a technology sense we would actually go in for what is referred to as forced convection. So therefore you would have either a fan or a blower or something that agitates this liquid system significantly, and in the process you are deliberately ensuring that there is a lot of mixing of the liquid. So whereas normally it might have taken several minutes for the temperature at the top of this container to reach whatever is the temperature at the bottom or very nearly that temperature, by forcibly agitating this liquid you can ensure that the top temperature reaches very close to the bottom temperature almost immediately. So therefore in an engineering sense forced convection is very important. And even if you look at a day to day example, so an air conditioner, okay, so in principle it could be putting out a very small amount of cold air very close to the air conditioner's exit, and then over a period of time the temperature in the room can drop. But again, as a technological thing, from the perspective of the comfort of the people in the room, you want the temperature of the room to come down quickly. So therefore you have a fan or a blower additionally in the air conditioning system, which then starts forcing the air into the room, and so therefore you get much better mixing of the air, the cold air and whatever is in the room, and in the process the temperature comes down. So convection is something, as I said, we associate with heat transfer occurring in liquids and gases, and it has lot of technological uses. So that is what it is. Conduction, as I said, largely it is the primary mode of transport of heat within a solid. Okay, so that is how conduction is seen as a, if you want to separate it and look at it. And then finally we have radiation as another means by which heat can be transferred from one position to another. And largely radiation is something that, where we are associating it with say with electromagnetic radiation. Electromagnetic waves. Okay. So in space, for example, the heat that we are receiving from the sun, between sun and earth we do not have any direct physical contact, so we do not have conduction between sun and earth. We do not have any since the atmosphere that we sense around the earth is essentially just within few hundred kilometers at most within the from the surface of the earth. For most part between earth and the sun there is no nothing, there is no atmosphere, there is nothing that resembles an atmosphere between earth and the sun in the distance that is there between the earth and the sun. So therefore we cannot really look in terms of convection as a process by which heat is coming from the sun to earth to the earth. So in fact the heat that does come from the sun to the earth comes in the form of electromagnetic waves and therefore is essentially using radiational processes. Okay, so radiation is what is being used to send us heat from the sun to the earth. Of course once it arrives at the earth to the extent that it heats up the atmosphere and then gets evenly distributed across this across the planet, a fair fraction of that is coming from convective processes within the atmosphere. Okay, so a lot of convection is occurring within the atmosphere to evenly distribute this heat across the planet. In fact, if you look at the difference between say a spacecraft out in open space as opposed to any of us standing on earth, because of the convective processes and so on which makes the temperature more uniform for us, we do not sense a big difference in temperature between the side of us that faces the sun and the side of us that is not facing the sun. Whereas a similar situation out in space where you do not have any other medium to evenly distribute the heat would result in a situation where the side of the spacecraft facing the sun would actually be significantly hotter than the side of the spacecraft which is in the shadow or essentially facing the dark side of the space. So therefore so that shows you that there is a I mean where these various processes are relative to each other and how they and locations and examples where these processes become important to us. So now what we are going to do is I just wanted to put this down because I want you to get a sense of what it is that we are looking at and perhaps what is the other things that are there which we are not specifically looking at the moment. So for our purposes of discussion we will focus more on the conduction process within the solid. Okay, so conduction is what we are going to look at. So the Drude model which we extend to the thermal property specifically to thermal to heat transfer in that sense, we are looking at the conduction process of heat transfer, we are not really extending it to convection or radiation. So already we are now looking at a subset of this process. Even here in the solid, as I mentioned, if you take a typical solid you can have a good conductor of a solid which has say a lot of free electrons present within it and is a good conductor of heat. There a vast fraction of the heat that is being transferred from the hot end to the cold end is occurring due to the movement of those electrons. Okay, so or they are the primary what to say mechanism or vehicle through which the heat is getting transferred from the hot end to the cold end. As I also mentioned, if you look at a more insulating type of a material, it is not, I mean it simply conducts heat in a much slower manner, but it does still conduct heat eventually. There the heat conduction is largely occurring due to thermal vibrations which we would also call phonons, but that is not something we are looking at immediately. So the manner of the process of conducting heat through thermal vibrations is not something that we are focusing on at the moment. So conduction itself could occur either through the movement of electrons or through these lattice vibrations exchanging energy from atomic position to an atomic position. Of the two we are only looking at the former case which is the electron movement. So we are not looking at these two modes, and in the conduction mode we are only looking at the electron transport process for transferring heat. So I just want you to have that complete picture, so that whenever you read an article or look at a book which is looking at a more holistic look at the thermal heat transfer process, you get an idea of what it is that we have actually focused on here, and what it is for which the equations that we develop apply to. Okay, so those equations do not cover everything, they cover a part of conduction that is relevant with electron movement, the heat conduction using electron movement. So but having cut it down so much, I would also like to emphasize that most of the time where you are looking at heat conduction and trying to utilize it to serve some purpose, you are actually utilizing materials where there is a lot of free electrons, and the heat transport is going to occur through the mechanisms that we are going to describe. So therefore from the perspective of heat conduction and good conductors of heat, the equations that we develop are quite relevant. So therefore it is, even though I am showing you what is the limitation or the framework within which we are operating and what are the things we are excluding from it, what we are including is reasonably significant, and therefore it is relevant and meaningful to look at it. Okay. So now we will go ahead and focus on conduction from the perspective of what it is that the electrons provide to this conduction process. Before we do that also, we will just additionally add, so from this from within this framework we will define conductivity or thermal conductivity. It is denoted by a symbol K. So thermal conductivity is, we will talk of this minus sign later, but it is basically the transport of heat. So some heat energy, so thermal energy in say joules per unit time, per unit cross sectional area, okay, and per unit temperature gradient. Okay, so you have some solid, you look at unit cross sectional area of that solid, and in that unit cross sectional area per unit time, what is the heat that is being transferred, and between 2 points, so x1 and x2 you have the temperatures between those 2 points are T1 and T2, capital T1 T2. So you have a delta T and a delta X, and this is the framework within this is what will give you the thermal conductivity. Okay. So if you look at this or if you rearrange this, we will get in differential form, we can write this as this term here is simply so therefore this is the heat flux which is the heat transferred per unit time per unit cross sectional area. So therefore we can write JQ dt by dx. This I have written in a one dimensional form, so that is why we just have x here, dt by dx is what we have. Okay, so this is one dimensional. This is referred to as the Fourier's law of heat conduction. Okay, so Fourier's law of heat conduction is what this is, fine. So so this is the quantity that we are interested in K, the thermal conductivity. Okay, so this is the quantity that we are trying to explore and get a value, get a sense for based on whatever is fundamental within that material, right. So so now we will focus on what we will do is we will start by actually looking at a one dimensional case, because this I mean, and it simplifies our analysis. So we will look at a one dimensional case, so we will only focus in the x direction, and later we will generalize it for 3 dimensions and then see if we can build first principles model, so to speak, or looking or based on something that is fundamental to the constituents of the material. We will try and build a model which helps us get us a value for thermal conductivity, and we will do this within the framework of the Drude model of the material, so to speak. Right. So now what we will do is we will actually look at this particular experimental case. So we now have a one dimensional solid, an example of a one dimensional solid. We have just put something down here, and we will say that this end of it is hot and this end of it is cold. Okay. So heat has to move from the hot end to the cold end. So this is the x direction. Okay. Fine. So this is the x direction. So now we would like to get a sense of how this process is going to occur and what are the parameters that are going to impact its occurrence. So the first thing we have is we see that there is a difference in energy from one end to the other. So we have a hot end and a cold end. So what we will say is and we will assume everything is linear. So what we see is the energy is actually a function of is effectively a function of temperature. Okay. So we are talking of thermal energy here. So the energy is a function of the temperature of that of whatever is the location. So at any given location, if you want to know what the energy is, you have to have a sense of what is the temperature at that location, then you have a sense of what is the energy. So energy is actually a function of temperature. Okay. So we will denote it like this. Now the temperature itself, because there is a hot end and a cold end, the temperature itself is a function of x. Okay. So T is a function of x. So energy is a function of temperature, temperature is a function of x. So therefore as a combined notation we will simply write it as E T x. So this is basic. So this is all that we mean. We have just combined all this information into this one notation. Energy is a function of temperature and the temperature itself is a function of x, the position, in this one dimensional sense. Fine. So so this is what we have. Now we would like to see how the heat is moving from the hot end to the cold end. We will just take some arbitrary location x. Okay. So this is the x direction of which we are taking one particular value of x, and what we will do is we will look at heat that is moving from the hot side to the cold side across x. We will also look at the heat that is moving from the cold side to the hot side across x. Essentially what happens in all these cases is, if you look at it from an atomic perspective, okay, all these transfers that are occurring, the atoms as such do not know which is hot, which is the hot side, which is the cold side, and so on. Okay. So even though we are putting down a hot side and a cold side and so on, in any process, whether it is heat transfer, whether it is diffusion and so on, in all these cases when you go down to the constituents of the material, there is no reason to believe that any of those constituents know exactly which is the hot side, which is the cold side. So what is actually occurring is that at any given location, movement is occurring in all directions. Things are moving from the hot side to the cold side, things are also moving from the cold side to the hot side. What we perceive from an experimental sense as heat transfer is now then the difference between the two processes that are occurring. Okay. So we something occurs from hot to cold, something occurs from cold to hot, you subtract the two, whatever is the net that is occurring is then the heat transfer that is occurring. Okay. So this is the same process, this is the same kind of situation that we would also have if you were talking of diffusion. You can have actually randomly atoms moving in all directions, there is a net movement of atoms in some direction, then you have a diffusional process. So the same thing we will look at here in the heat transfer process. So we would like to see what is the heat that is going from this side to this side. We would also like to know what is the heat going from the cold side to the hot side. Okay. So to do that, what we want to know is to see what is the energy that is crossing over the x, this location x from the hot side. We want to know what is the energy of that set of electrons which are now arriving at x. Okay. So that then determines what is that energy that is crossing the x direction or this particular interface, this particular location. Okay. We discussed in our last class within the framework of this model that you have a certain mean time between collisions for the various electrons. Okay. So that mean time between collisions we designated as tau, right. So this mean time between collisions is of significance in our discussion right now, which we will see in a moment. The other thing we also mentioned within the framework of this model is that the electrons exchange energy with each other only by means of collisions. Okay, so that is the primary and only, in fact the only mechanism by which they are exchanging energy with each other. So when I say that energy is moving from the hot end to the cold end, it is occurring by a series of collisions where electrons which are close to the hot end have an energy corresponding to that higher temperature that is there at the hot end. They collide with electrons which are little further away, which had actually a lower temperature. They convey some of their energy to that electrons which are now at a lower temperature, which pick up this energy as a result of that collision, and then that process continues, and that is how the heat gets transferred from the hot end to the cold end. So if you want to know what is the energy of the electrons which are arriving at this interface, at this surface or this particular location from the hot side, actually what it is that we are looking for is where was the last collision that the electrons had before they came to this location. Okay. So if you, since the mean time between collisions is tau, any electron arriving at x on average has had a collision at x minus has had a collision tau seconds earlier. Okay. So and given that its velocity is v in the x direction, let us say its last collision at v tau. Okay. So so an electron arriving at x from the hot side has had its last collision at x minus v tau. Okay. Last collision was v tau away from this location, it occurred at tau seconds before this location, and so the last collision v tau before x. In other words, the last collision that that electron had was at a position x minus v tau. Okay. So the collision occurred tau seconds earlier, at which point it was v tau distance away from x in this direction, and so the actual position, the coordinate of that position in the x direction is x minus v tau. Now if you look at our notation, the energy the temperature corresponding to that location would be T of x minus v tau, and therefore the energy corresponding to that would be E of T of x minus v tau. Fine. So energy of the last location where the collision occurred is simply E of T of x minus v tau, right. So for a given electron which arrives at this position x from the hot end, the position where it got its last collision was at x minus v tau, and therefore the temperature there was T of x minus v tau, and therefore there is an energy corresponding to that. Fine. Now so we have this arbitrarily, I just mark this here, x minus v tau, x minus v tau. We also within the framework, so we are now using parameters that are relevant to this model, which is for example in this case v, and this is tau. The other parameter that is of interest to us is the number of free electrons per unit volume, which is Nf. Okay. So and since we have a certain number of free electrons per unit volume, that is the same number of free electrons per unit volume across this entire length. Okay. So now at this location, if you consider a unit volume around this location, you have Nf free electrons available per unit volume. Of these and all of them are having this energy corresponding to this location, and since the movement is random, half of them could continue moving towards the hot side and half of them would continue moving towards the cold side. Okay. So we will have Nf by 2 electrons per unit volume moving towards the moving towards x. Towards the position x. Okay. And their velocity is v. We said that the velocity is independent of position, again something which is within the framework of this model. So therefore the flux of heat Jq from hot to cold equals okay. So we have these many electrons per unit volume moving with this velocity and having this energy. So that is the number of electrons having this velocity and with this energy, that then if you take the product then you are looking at the energy being transferred from the hot end to the cold end per unit area. So this is the flux being transferred across this sort of across this system. Okay, so so this is what we have. If you want to check, so this is number of electrons per unit volume, so per meter cube, this is meters per second and this is joules. So joules per meter square per second is what you have. Okay, so therefore dimensionally it works out appropriately. So now the same thing we can actually look at this image here, and we will see what is the energy that is being transferred from the cold side to the hot side. In other words, what is the energy of the electrons which are arriving at X but from the cold side. Those are the electrons which will now cross it from the cold side. So for them the exact same analogy will same set of reasonings will hold, except that their collisions would have occurred at tau seconds before away from this interface. So in other words, at x plus v tau. So the electrons arriving at this location x from the cold side would have had their last set of collisions at x plus v tau. Okay, so so that is where their collisions would have occurred. In a very similar or analogous way, we will say that they are again arriving here with a velocity v, and we have a number of free electrons per unit volume is again nf. It does not really matter whether you are the hot side or the cold side, that is again fixed for the system. So we have a number of free electrons is nf. Again from this location, half of those free electrons can continue moving towards the cold side, half of them could continue moving towards the hot side. The point of this half is that it is a random process, right. So given that they are all sitting there with that energy, they could either go left or they could go right. There is nothing, we are not giving any preferential treatment that it has to go right or it has to go left. It is a random process, it could go either which way it could go, and it is a one dimensional sense, so we have two options available to us, right or left. So we just say that for sake of keeping it random, we say half of them moved that way, half of them moved this way. So again the same reasoning would hold true. We would have the energy of the previous collision, of where the previous collision occurred, would be E of T of x plus v tau, and therefore the J cold to hot, so energy being transferred from the cold side to the hot side through that interface x. We are now bringing all this down to that interface x. At that interface x, what is moving from hot to cold, what is moving from cold to hot. What is moving from hot to cold is simply what arrived from the hot end to that interface, and whatever is moving from cold to hot is simply what arrived from the cold end to that interface, and what arrived came from the immediate previous collision. So that is the body of information that is being contained within this equation. Okay, so cold to hot is nf by 2 v and E times E of temperature T, which is a function of position, and in this case the position of interest is x plus v tau. So that is the thing we have. So we now have two pieces of information, energy moving from the hot side to the cold side, and also energy moving from cold side to hot side. We have expressions for both. So what we simply have to do is we want to look at the net transfer of heat. So we simply are going to subtract these two expressions and get ourselves an expression for the net transfer of heat, right. So we have an expression for the transfer of heat from the hot side to the cold side, and separately an expression for the transfer of heat from the cold side to the hot side across that interface x. So we will now subtract the two and give ourselves a net transfer of heat. So J net hot to cold equals simply J hot to cold minus J cold to hot. Okay, so this is nf by 2 v E of T of x minus v tau minus nf by 2 v e of t of x plus v tau. Okay. So, this is what we have. So, we will rewrite this in a way that is convenient to us, nf by 2 v of e of okay. So, this is what we have. So, we can write a given E. So, we will write E t, we can write E of t of x minus v tau as simply approximately equal to E of t of x minus v tau dE by dx. Okay. So, this is simply the energy at the position x. Okay. So, we are looking at the energy at position x minus v tau, and we are sort of approximating it for very small variations, for very small delta x we assume some kind of a linear variation in energy. We are saying that at the position x minus v tau, it is the energy that is there at that position x minus or plus or minus whatever is that distance that you have to travel to get to that position, in this case minus v tau dE by dx is the gradient. So, change in energy as you move from position to position. Okay. So, we simply make this say approximation of linearity, so to speak, and so E of at position x minus v tau is simply the energy at position x plus or minus dE by dx times that position, the displacement from that position, which is v tau. In this case it is minus because it is x minus v tau. Similarly, E of x plus v tau would similarly be E of t of x plus v tau dE by dx. Okay. So, plus dE by plus in this case because we have plus v tau and minus because we have minus v tau. So, we can make these approximations and then substitute back into this equation. So, therefore, J net hot to cold equals nf by 2 v. You will have we will just write it down fully so that it is clear, E of t of x minus v tau dE by dx minus E of t of x okay. So, this is actually E of t of x plus v tau dE by dx, but we subtract the whole thing out, we have to put a minus sign here, therefore, you get a minus sign in front of this entire term here. So, this minus sign would come in front of this as well as here. So, this is what you have put down here. So, these will go. So, therefore, you have and okay. So, you have nf by 2 v times 2 v tau dE by dx, and please note we have put dE by dx actually, as we said, for us to be more specific about what we have here, energy is a function of temperature, which is then a function of position. We have directly written energy, we have taken the derivative with respect to x, we should actually take it as with respect to t, which will then be again derived differentiated with respect to x, and we have a minus sign here. Okay. So, minus v tau we have that. So, minus 2 v tau. So, this is equal to nf v square 2 would go tau dE by dx, okay, minus nf v square tau dE by dx. So writing it again, we will have minus NF V square tau dE by dt by dx. Okay, so this is what we have as the net flux of heat from the hot side to the cold side. Okay, if you simplify following everything that we have simplified, we have written it down this way. Now if you see, in a way this has been written for this dE by dt, this energy at a given position and so on has been written with respect to a single electron, but the total number of electrons per unit volume has been taken into account using this term NF. So this NF dE by dt, NF dE by dt okay, this is the change in energy for unit change in temperature. Okay, so that is what it is for the entire number of electrons per unit volume. So this is simply your specific heat at unit volume associated with the electrons. Okay, electronic specific heat at per unit volume, number of free electrons per unit volume times the change in energy per unit change in temperature for a given electron. So if you take that into account, this is the specific heat per unit volume. Fine. So therefore we can put that here. So we will do that here. J net hot to cold equals minus, we just put that down here, minus NF V square tau dE by dt and dt by dx, and we have identified NF dE by dt to be CV or specific heat per unit volume associated with the electrons. So this is simply minus V square tau CVE dt by dx. So we have now almost gotten to where we wish to get. We just need to generalize it just a little bit more, and then we will have an expression the way we would like it to, the way it, in a manner that would be useful for us. The first thing is this velocity here, we cannot, I mean, as we have done before, the velocity that is of relevance to us is the mean velocity, so mean of the squares of velocities that are present in the system, because then that would be representative of the electrons present within the system. So whereas we started off all of this by just using a certain velocity, this is actually the mean of those velocities. And the other thing is we have actually done this effectively in one dimension, so to speak. So we would need to extend this to assuming that the electrons could actually move in 3 different directions and not just in one direction. So the net transfer in any one direction would be 1/3, because it is equally randomly possible for the heat to be transported up or down, left or right or back, or I mean, or to the front of the board or behind the board. So we will take these two into account. So taking 3 dimensions into account, we will actually have J net equals 1/3, minus is there, minus 1/3 V square, this brackets being put in to indicate that this is the mean that we are looking at, tau CVE dt by dx. Okay, so we have this expression, and we also wrote down J equals minus k dt by dx as the Fourier's law. For heat conduction, okay, Fourier's law for heat conduction, we wrote J equals minus k dt by dx. So first of all, we now have 2 expressions where you have the heat flux on your left hand side, and you have dt by dx available for you in both cases, and then you have k in one expression, and then a bunch of other parameters here, which then of course imply that they are the parameters that give us the conductivity k. I will also again I just want to take this opportunity to point out that this minus sign comes simply because of the way in which we define the direction of temperature gradient. Normally any gradient will go from low to high. Okay, so so when you have a cold end and a hot end, so the temperature gradient is the increasing direction of the temperature is from the cold to the hot, whereas the heat flows from the hot to the cold. Okay, so therefore when you are looking at heat flux, it is in a direction that is opposite to the positive dt by dx, therefore you get this negative sign. So that is where the negative sign comes from, because it is in this direction is opposite to that direction, hence the negative sign. Okay, so minus k dt by dx. So therefore now comparing these two expressions, we get the thermal conductivity k is now 1 by 3 v square tau CVE. Okay, and if you want to look at the units, this is going to be meter square per second square, tau is in seconds. Okay, this is specific heat at constant volume for the electronic contribution to the specific heat at constant volume. So this is joules per constant volume is meter cube, and it is specific heat means per joules per Kelvin. Okay, so for every degree rise in temperature, what is the heat that is required? So joules per Kelvin per meter cube is the unit that you have here. So therefore if you look at this now, this is then joules per meter or joules per second per meter per Kelvin. Okay, so meter square meter cube will give you meter minus 1, second square will give you second minus 1. Okay, so joules per second per meter per Kelvin. So you could also write it as watts per meter per Kelvin. So that would then be the units for your thermal conductivity. Okay, so now we have an expression for thermal conductivity, and if you look at values that are available to you, this v square is of the order of 10 power 10 meter square second square, meter square per second square. Tau is of the order of 10 power minus 14 seconds, and CVE is of the order of 10 power 6 joules per meter cube per Kelvin. Okay, so if you take these into account, we are looking at roughly about 10 square, we get k approximately equal to 10 square joules per second per meter per Kelvin. Okay, so we get this value for thermal conductivity. So what we have done is we have looked at the Drude model, we have developed a set of equations that take the basic ideas of the Drude model, all those concepts such as mean free time between collisions, the number of free electrons per unit volume, all those specific ideas that are relevant to the Drude model are taken, and with respect to those ideas we have looked at what heat is transferred from the cold side, from the hot side to the cold side, what is being transferred from the cold side to the hot side, what is the net transfer of heat, and come up with an expression then that has all the attributes of this Fourier's law of heat conduction, and by comparing the two we are able to pull out an expression for the thermal conductivity, and based on values we are able to locate for the various parameters that are there in that expression. We have about 10 square joules per second per meter per Kelvin. If you compare this with what is available in the literature for good conductors of heat, especially good metallic conductors which are then good conductors of heat, so silver, copper and gold for example, if you compare them you will find that their conductivity, thermal conductivity also comes out to the same order of magnitude. It is of the order of 10 square joules per second per meter per Kelvin. Specific values vary, but at least order of magnitude, as I said, which is the primary parameter of interest for us, comes within the correct range. Okay, so what we have done in this class is we have looked at thermal conductivity, extended the Drude model to see how well it addresses thermal conductivity, and we find that we are able to come up with an expression for thermal conductivity, and the value that it is predicting, is reasonably okay for some of the metallic systems that we may come across in the engineering and technological sense. Okay, so so with this we will conclude our discussion at the moment about thermal conductivity. So what we have done in the last class is the Drude model for the electronic conductivity of the material. today we have done the Drude model for the thermal conductivity of the material, and I also placed in perspective where this thermal conductivity is with respect to all the heat transfer processes that are available to us, and even within the conductivity process with respect to say phonon based conduction of heat versus electron based conduction of heat. What is the process that we are, what is the framework and what is the specific region of study that we are focusing on. So within that framework we have come up with an expression. So we will halt here today. In the next class we will take up comparisons of these two conductivities that we have developed, electronic conductivity and thermal conductivity, and how these properties actually relate to each other for various materials, and what does this model tell us about such a relationship, and therefore how reliable it is in terms of other predictions that it makes. Okay, so with this we will halt for today. Thank you.